exponential function. So this is the first time in math you've seen something like this. Anyways, so let's look at the characteristics of what makes up an exponential function. So a function where the exponent is a variable. That is the reason why it's considered an exponential function. So c is the base. C has to be greater than 0, and it can't be 1. If c was 1, then I would get f of x, which is just a fancy name for y, is equal to 1 to the power whatever. Well, what's 1 to the power whatever? 1, it's always 1. So basically, I'd be graphing a constant function, right, a horizontal line. So that's why c can never equal 1. Why do you think c would have to be positive, though? And it couldn't be negative. Yeah, it would be an oscillating function, meaning it would go from positive to negative, depending on what the power was, right? So that would not make up an exponential function. So let's graph y equals 2 to the power x. So this is where you were supposed to review how to do exponents. So again, I'm going to plug in -2 for the exponent. So what's 2 to the power -2? Maybe I don't have any really room here, but 2 to the power -2, you're supposed to remember how to deal with negative exponents. And what do you do with it? You reciprocate it, so then it becomes 1 over 2 to the power +2. Yeah, and then you square the 2, so you get 1/4. Okay, what would 2 to the power -1 be? 1/2, because again, that would be 2 to the power -1, which would be 1 over 2 to the power +1, which makes 1/2, yes? What's 2 to the power 0? 1, you learned that property back in grade 9. 2 to the power 1? 2 to the power 2? 4 to the power 3? 8, not 6. Okay, so let's plot these. So of course a quarter, just kind of make your rough estimate here. We just want to see the general sketch of this. So -2 a quarter, say just a little bit above, -1 1/2, then 0 1, 1 2, 2 4, 1 2 3 4, and then 3 8. So that's 4 5 6 7 8. I don't know why I have a dot over here. I'll erase that. Okay, so this is a nice curve. So what happens is it's going to go like that. It's an increasing function. And what else could you tell me about it? What happens on the left when the exponents get really big negative? You're going to get a really small number. When it approaches a really small number, what number would that be? Huh? 0? Yeah? So that's asymptotic behavior, right? It's getting closer and closer to 0 without actually being 0, right? Because how could you have an exponent equal to 0 unless the base was 0? So all graphs, oh, I have to do the next one before I can start saying some of the properties here. So let's do 3 to the power now. So when it's 3 to the power -2, what would that be? Huh? 1 over 9, very good. What about 3 to the power -1? 1 over 3. What about 3 to the power 0? 1. What about 3 to the power 1? 3. 3 to the power 2? 9. Okay, so I'm going to do it in a different color pen just so I can show the difference. So -2, it's 1/9. So it's below the blue one, right? -1 1/3, it's below the blue one. It's right on the money for 0, 1. And then what happens after that? It actually is above the blue line now, right? And at 2, it's at 3. So do you see it's below before it crosses the y-axis, and then it starts increasing really fast. Y equals 3 to the power x. And then I'll label my blue one here. This is y equals 2 to the power x. What do you think would happen if it was y equals 10 to the power x? Yeah, it would look the same. It would be, but it would go increase really fast, right? Yeah? Okay, so what are the characteristics of these graphs? Well, all graphs pass through the point 0, 1. Does that make sense to you why they would all pass through 0, 1? Yeah, anything to the power 0 is 1. I say that with a grain of salt because once we go into calculus next year, you'll find that 0 to the power 0 is not equal to 1. Infinity to the power 0 is not equal to 1. So like I said, anything except for those kind of things to the power 0 is 1, but these are indeterminate forms. So you can't actually calculate that without some calculus going on there. Okay, does everybody see in both graphs that the graph has no x-intercept? Yeah? What's the domain? All reals, yep. So negative infinity to positive infinity. What's the range? Does it include 0? No, so it's a round bracket on 0 and it's going to infinity. Although it looks like at some point the x's don't, like, do you see, because it increases so fast, it's almost like you think there's nothing here. But if you drew a big enough graph, you could have x's a million for an exponent. It would be a pretty big number if it was a power, but you know, if we had all the number system to deal with, there'd eventually be something like that. Okay, there exists a blank asymptote at blank. What is that? Horizontal asymptote at, that's not, although I know what you're trying to say, that is not the correct way to say it. It's not the 0 at y equals 0. You could say at the x-axis. You could say at the x-axis. That's what I'm saying. On the test where people describe things, I know what you're trying to say, but you're not actually saying it clear enough for somebody to walk off the street and know what you're talking about, right? So you always got to think, I need to describe this well enough so that somebody walking off the street could actually figure out what I'm saying, right? The last property is it's increasing when the base is greater than 1. We don't know that it's decreasing yet, but I'm giving you the property right now that it's decreasing when it's between 0 and 1. Remember that c cannot be negative, so it has to be between 0 and 1. So now we're going to look at this and see that it'll be decreasing. So if it's 4 to the power negative 2, what do we get? 1 over 16. 4 to the power negative 1. 1/4. 4 to the power 0. 4 to the power 1. 4 to the power 2. 16. We're going to plot that. So again, it's by the way, although it has a 10 here, I haven't labeled my x and a y, and we need to get into the habit of doing that because that would be an error. It has a 10 labeled. It doesn't have an x label, so I'm going to put a 1 there. You need to have a scale. I don't know why the scale in the x and y axis was not labeled to begin with, but let's just put it there so we have no errors. So negative 1 1/4, it goes through 0, 1, 1, 4, 1, 2, 3, 4, and then of course 2 will be off the thing here. So 10, 11, 12, 13, 14, 15. It'll be like way off there. So if you want, you can just go straight up. Just so you know, if you do not label the asymptote, it will be, it will not be an error, it will be an actual deduction. So although it's the x-axis, in order to indicate it, just put it past where the left axis goes so you can actually see it, right? Because some people put it on the axis and because the axis is already black, you can't really see it. Just so you know, and I know up into this point, asymptotes have usually been the entire coordinate plane, but you'll see more and more of these graphs. They only have asymptotic behavior in certain regions. So for instance, it's asymptotic behavior where x is big negatives, right? It's not where x is big positives. So it doesn't make sense to make an asymptote going across the whole thing. Do you see what I'm saying? And you'll get graphs next year in calculus where you'll have an asymptote here, then it goes like this, and then maybe it has an it'll be a vertical asymptote, and then it'll go like, say, that, and it'll level off here, and then you'll have an asymptote here. So do you see? You'll have an asymptote way up here, and asymptote, like you'll have all these goofy graphs. So I guess what I'm trying to get in your mind, that asymptotes aren't necessarily throughout the whole graph for x's, okay? Obviously for y's, this shows that it's never the case. But I know, I'm pretty sure, grade 11 last year, you had, you had a graph that looked like this. I'll erase this after. Where you had 3 regions, and it went like this, right? And then it went like, say, that, and like that. Do you see? So although you think the asymptote goes through the whole thing, it was only asymptotic behavior right here and right. So big x's and big negative x's. It wasn't going through the whole thing. Does that make sense to you? Okay, so I'll erase all that stuff. Okay, so let's do the next one. Y equals 1/4 to the power x. So what do you do when you have 1/4 to the power -2? You reciprocate it, so you get 4/1 to the power +2. So what does that end up being? 16, yes? -1 would become 4, 0 would still be 1, 1 would be 1/4, and 2 would be 1/16. So I'm going to actually do that in red again. Okay, so -2 would be 16, which was way up there, right? -1, 4, 1, 2, 3, 4, 0, 1, and you have 1/4, 60. So it's increasing really high. This is where there is an error code for asymptotes where if you have a graph that goes towards an asymptote and then you have it curling away, it goes like this, just because that's exaggerated. But if you do that, you will lose an error code. It's E10 or something like that. Anyways, so make sure when it hugs the asymptotes, don't make it go back up. Just hug it, stop it, right? What do you notice about these two graphs? Besides that, when you have 1/4, it's now a decreasing function versus an increasing function. Anybody notice anything here? They're a reflection over the y-axis. Why do you think that's the case? Right. Do you know another way I can write 1/4? 4 to the power -1. Does everybody see that? Does everybody see that 1/4 is the same thing as 4 to the power -1? So this is the graph of 4 to the power -x. Do you remember all those things we learned in the first unit with transformations? That's going to come into play. So we have a base exponential graph, and then the -x meant that we reflect over the y-axis, right? So anyways, now that you know that, you can do it that way. Okay, so here's a base graph. Can you come up with a pattern here? Well, it crosses at 0, 1. Yes? What about here? 1, 5. 2, 25. Does anybody think they know what this equation is?
5x.
5 to the power x, not 5x. So that would be a line. Do you see what I'm saying about descriptions matter? 5x and 5 to the power x is not the same thing, right? Okay, so here's where science comes into play here. Exponential functions can be used to model many real world phenomena such as exponential growth. Oh, I spelled exponential wrong. Let's try that again. Actually, I don't want exponential growth. I want population growth. Comma, the growth or decay of various substances. Anybody in chemistry did carbon dating at all? Like where we talked, oh, you talked about it. So when you talk about half-life, that's how they date like archaeological things, or they find something, they can measure how much carbon's in it, and they know how much carbon decays and how much something brand new would have for carbon or whatever, and somehow they figure out what the age of it is based on that. And they use math to do that. Yeah. Another one is, and we'll do more about this later, but this is the first exposure. Just so you know, kids start learning this in grade 11 essentials. This same question. Initial investment of $4,000 earns interest of 4% compounded annually. So whenever you get a chance and you think about courses to take and stuff, I know some people put their nose up to essentials, but it actually has a lot of real life applications. And this is one that we get to see in pre-cal as well. But like I said, you waited till grade 12 pre-cal till you actually saw like almost a real world application here. Because there's so much stuff to learn first before you can apply it, right? Okay, so does everybody see what's happening here? You invest $4,000 and you're getting 4% each year. So let's do a table of values for the first 10 years. So this would be investment amount, and this would be the number of years. So at year 0, we have how much money? $4,000. So the amount is dollars. Okay? What happens at year 1? After year 1? We're getting 4% more, right? So how do we figure out 4% more? 4% is what as a decimal? 0.04. Yes. Okay, so if you've never seen this before, you don't realize that if you just multiply 4,000 by 0.04, you just get the amount of interest. You don't actually get how much your investment is, right? So does everybody understand? You don't just have 4%, you have the 100% that you had from before. So really, if you have the 100% and the 4%, you actually have 104% of the value that you had the previous year. Does that make sense to you? So we're actually using 1.04 as our multiplier. And so if you get your calculator out, you did? Right on. Oh, that's how you knew that it was 1.04. So you got 4160. Did everybody see that? Yes? Year 2. Do I take 4,000 again? No, now I have the previous years, right? And I'm getting 4% on top of that. So I'm taking the 4160 and timesing it by 1.04. And I get $4,326.40. Now, this is what people call the power of compounding. Because now you're not just making money on the $4,000. What's happening now? You're making money on the money you made from the interest. So the interest is now getting more interest. This is why financial advisors will say to you, as soon as you can, start investing in your RSPs. So if you graduate with a degree, say, and you're 24 years old, start putting your RSPs away, because then by the time you're 55, it would have been in there for, say, 30 years. And the power of 30 years, you'll see, is quite a bit. Okay, so we could keep going, and I don't know if we really need to see what's going on here more. How could I figure out what it would be in 10 years without actually doing each year individually? So for instance, what was this first equation here? I went 4,000 times 1.04. I got that answer, which is 4,000 times 1.04, and then what did I do again? I times it by 1.04. Does everybody see what's happening? So in year 2, how could I write that? I'm not going to write this as this times this. It's really 4,000 times 1.04 to the power 2. Do you see that? So what do you think it would be in year 10? 4,000 times 1.04 to the power 10. So do you know how to punch that in your calculator? There is a y to the x button, or you might have a little, I call it a caret. Yes? That's the actual word on the keyboard for it, is a caret. Some people even have an x to the power y button. So 4,000 times 1.04 to the power 10 gives me $5,920.98. Now, electronic world, we do have pennies, so all of our answers will be rounded to the nearest penny. This would be the exception to the correct to 3 decimal places. What happens if I want, I think that this is when you guys were 25. Let's pretend Grandma gave you a graduation present of $4,000 at 18, okay? So she gives you a graduation present of $4,000 and you're a good kid, you're going to save for the future. Maybe she puts it into an investment for you, so you can't touch it until you're 55. So you're 18 and 55, that's 37 years later. Let's figure out 37 years later. So that would be 4,000 times 1.04 to the power 37. Wow. $17,072.36. You did not do anything. Grandma gave you this at 18. You left it. Now you have $17,000 by doing nothing. This is the power of compounding.